Okay, so on to question 9. This is an antenna pattern or antenna chart that we need to be able to read. So the first thing they want us to find is the beam width. Keep in mind that the rings are not always a -3 change. So this first one is -3, -6, then it jumps to -12 and -24. Or it's not showing some of the rings, I'm not sure which. So to find the beam width, the first thing we do is we figure out where the beam pattern for the main lobe, so the one that hits 0 degrees on the chart, we figure out where that hits -3 decibels. So this first inner ring is -3. So we draw points here where it intersects with this small alien shape for the antenna. Then we draw a dotted line out through that point and do the same thing for the one on top. And then we can measure the angle from 0 on each side of this. We'll say this is roughly, somewhere between 20 and 30, maybe 25 degrees on each side. Sorry for my writing. So in total, beam width is going to be 50 degrees because we're measuring the total distance across this arc here. And so if it's 25 on each side of it, it's going to be 50 total, roughly. So side lobe level. Side lobe, we are measuring any side lobes like this one and like this one, determining where they are. And then our equation is side lobe level is main lobe level minus side lobe in decibels for both of those. So we're going to measure that the side lobe is somewhere at approximately, it's a little between 12 and 24. So maybe it's a little closer to 12. I think the solution says that it's at roughly 15. So we'll say it's at -15, which means 0 minus -15 is 15 decibels. Your side lobe level and front back ratios should always be positive numbers, so do not leave them as negative. You're going to measure a negative decibel value and then subtract that negative decibel value from 0, which is going to give you a positive number. Same thing for front to back, so we're looking at 180 here. And we're going to measure to see exactly where that is. It's somewhere between 12 and 24. It's about equidistant, so we'll say that it's at 18. So this is main lobe level minus front back level. So that's 0 minus -18 is 18 decibels. Again, this should always be a positive number. And then finally, physical size of the driven element. So here we need to read the question and see that our antenna transmits at 400 megahertz. The driven element of a Yagi antenna is lambda over 2, or wavelength over 2 in size because it's a dipole antenna. So we have that, and we need to find what wavelength is. Wavelength is C over F, which is 3 times 10 to the 8th over, in this case, 400 times 10 to the 6th, which is going to be 3 over 4 is 0.75 meters. So then length is 0.75 meters over 2 is 0.375 meters. Okay. If someone is standing in a life raft with a handheld VHF radio, assume antenna height of 6 feet, what is the maximum range from which they could contact a search and rescue helicopter flying 100 feet above the surface? So this is using the equation D equals square root of H1 plus square root of 2H2. So in this case, H1 is 6 feet, so square root of 2 times 6 plus square root of 2 times 100. So we're just finding the feet in the equation, or in the word problem that we're given. And that's going to be equal to approximately, I lost it on my sheet here, 17.6 miles. Keep in mind again that these numbers are in feet. The output of this equation, D, is in miles. So do not mix up those units. Question number 11. Your Boost mobile cell phone transmits with a power level of 200 milliwatts, an antenna gain of 2.15 decibels, and a frequency of 850 megahertz. Messing up all my numbers here. The cell tower to which you are connected has an antenna gain of 0 decibels. How far can you be from the tower while maintaining the capability to communicate? Assume a dead zone occurs when PR is less than -90 dBms. Okay. So this is where we need to use the freeze equation. So PR equals PT GT GR lambda squared over 4 pi D squared. In this case, we're trying to solve for how far we need to be, the distance from the cell tower in order to lose power. And we can kind of figure out, right, that our cell phone is transmitting with a power level of 200 milliwatts, so PT equals 200 milliwatts. We know that PR is in decibel milliwatts, so whenever we convert negative 10 to the negative 90 over 10, which is 10 to the negative 9, that's going to be in milliwatts as well. So we have PR, which is our power received. We have PT, which is our power transmitted. We have GT is going to be 10 to the 2.15 over 10, because we want this to be unitless gain for the Friese equation. Remember, the P terms need to be in watts or milliwatts, both matching. The gain terms need to be in unitless gain, not in decibel gain. GR is 10 to the 0 over 10, which is just 10 to the 0, which is 1. And so we have that term, and we have lambda, because we have lambda equals C over F is 3 times 10 to the 8th over 850 times 10 to the 6th, which is going to be roughly, lambda is roughly 0.353 meters. Okay, so we have all of these terms. The only thing we aren't given is distance, which means that's what we're solving for. So d squared equals PT, GT, GR, lambda squared over 4 pi squared PR. This is just moving PR over to here by dividing, moving d squared over to there by multiplying. And so then we have d is equal to square root of PT, GT, GR, lambda squared over 4 pi squared PR. Okay, at this point, it's just plug and chug. You need to take all of the terms that were given here, add them, or plug them into the equation, and use your calculator properly, and that should give you the distance is 16.091 meters, or approximately 16.09 kilometers. Okay, and that's it for that page.